Cartesian equation of a line using direction ratios. Welcome, everyone. Today, we are moving on to a new topic, the Cartesian equation of a line using direction ratios. Now, before we dive into the new material, let's take a moment to reflect on what we have already covered. In our previous subsection, we explored the parametric equations of a line. As you know, those equations are incredibly useful when we want to find specific individual points along a line. However, there is a slight limitation. They rely on an auxiliary parameter, which we usually call lambda. In this lesson, we are going to learn about the Cartesian equation. This form is quite powerful because it provides a much more direct relationship between the coordinates x, y, and z, allowing us to describe the line without needing to worry about that extra parameter lambda. Understanding the concept. Now that we know we are moving from parametric to Cartesian forms, let's look at the core concept behind this transition. Think of the Cartesian equation as a streamlined version of what we've already studied. Essentially, it is a way to describe the line by eliminating the parameter, lambda, from our parametric equations. We want to get rid of that extra variable so we can see the direct relationship between x, y, and z. To do this, let's quickly recall our starting point. Remember, the parametric equations for a line passing through a specific point, P with coordinates x sub 1, y sub 1, and z sub 1, and which is parallel to a vector with direction ratios a b and c, are written as x equals x sub 1 plus lambda times a, y equals y sub 1 plus lambda times b, and z equals z sub 1 plus lambda times c. In the next few slides, I am going to show you the algebraic steps we take to isolate lambda and merge these three separate equations into one single, elegant Cartesian equation. Step-by-step derivation. Now that we understand the fundamental concept of how the Cartesian equation relates to the parametric form, let's move on to the actual derivation. We are going to break down the transition from the parametric form to the Cartesian form into a few manageable, logical steps so you can see exactly how the parameter lambda disappears. Isolate \lambda dollar in the x dollar coordinate equation. Now that we have established our starting point with the parametric equations, let's begin the actual derivation. In this slide, we are going to focus specifically on the x-coordinate. We start with our first parametric equation, which is x equals x sub 1 plus lambda times a. Our goal here is to isolate the parameter lambda. So, the first step is to subtract x sub 1 from both sides of the equation. This leaves us with x minus x sub 1 equals lambda times a. Next, to get lambda by itself, we divide both sides by a. Just a quick note here. We must assume that it is not equal to 0 to avoid division by 0. Once we do that, we arrive at lambda equals the quantity x minus x sub 1, all over. We will repeat this exact same logic for the y and z coordinates in the next few slides to eventually link them all together. Isolate \lambda dollar in the y dollar coordinate equation. Now, just as we did with the x-coordinate in the previous slide, let's apply that same logic to the y-coordinate. We start with our parametric equation for y, which is y equals y sub 1 plus lambda times b. To begin isolating our parameter, we'll subtract y sub 1 from both sides of the equation, which leaves us with y minus y sub 1 equals lambda times b. Finally, assuming that b is not equal to 0, we can divide both sides by b. This gives us an expression for lambda, where lambda equals the quantity y minus y sub 1 all over b. We'll perform this exact same process for the z-coordinate in the next slide to complete our derivation. Isolate \lambda dollar in the z dollar coordinate equation. Now, we apply this exact same logic to our third dimension. Just as we did with the x and y coordinates in the previous slides, let's look at the z-coordinate equation. We start with z equals z sub 1 plus lambda times c. To begin isolating our parameter, we subtract z sub 1 from both sides of the equation, which leaves us with z minus z sub 1 equals lambda times c. Finally, assuming that c is not equal to 0, we divide both sides by c. This gives us the expression for lambda equals the quantity z minus z sub 1, all over c. Once we have these three separate expressions for lambda from our x, y, and z equations, we will be ready to move to the next slide and equate them to form our final Cartesian equation. Equate the expressions. Now, this is the most crucial part of the derivation. Up until now, we have been looking at the x, y, and z coordinates individually, and in each case, we isolated the parameter lambda. But remember, lambda is not just any random number. It is the same constant value for any specific point we choose along this line. Because each of our three previous equations, the one for x, the one for y, and the one for z, is all equal to this same lambda, it logically follows that we can set all three of these expressions equal to one another. By linking them together, we get x minus x sub 1 all over a equals y minus y sub 1 all over b, which equals z minus z sub 1 all over c. And there we have it. By eliminating the parameter lambda, we have arrived at the Cartesian equation of the line. This single, continuous equation now directly relates our coordinates x, y, and z without needing that extra auxiliary variable. Real-world analogy. Now, before we jump into the mathematical calculations, let's take a moment to visualize what we have actually derived. Sometimes, looking at all those fractions can feel a bit abstract, so let's use a real-world analogy. Imagine you are in a dark room and you turn on a laser beam. To describe the path of that laser beam mathematically, we need two specific pieces of information. First, think about the point x sub 1, y sub 1, z sub 1. This represents the exact location of the laser pointer itself, the source of the light. It is our starting position in space. Second, we have the direction ratios, b, and c. These represent the direction in which the laser is pointed. They tell us the orientation of the beam, indicating exactly how it is angled through the room. By combining these two elements into the Cartesian equation we just derived, we gain a powerful tool. This equation allows us to take any other point in the room, which we can call x, y, and z, and mathematically determine if that point lies exactly on the path of that laser beam. With this conceptual understanding in place, let's move on to a practical, worked example to see how we apply this formula to a real problem. Worked example. Now that we have understood the theory and the derivation behind the formula, let's put it into practice with a concrete example. Here is a problem for us to solve. Find the Cartesian equation of a line that passes through the point A with coordinates 3, -2, and 5, and is parallel to a vector with direction ratios 2, 4, and -1. We will break this down step by step in the next few slides to ensure we apply the formula correctly. Solution breakdown, step 1. Now that we have the formula ready, let's move into the practical application. In this first step of our solution, we need to carefully identify the given values from the problem statement. Looking at our problem, we are told the line passes through point A, which gives us our coordinates. X sub 1 is 3, y sub 1 is -2, and z sub 1 is 5. Next, we look for the direction ratios, which tell us how the line is oriented in space. From the problem, we can see that A is 2, B is 4, and C is -1. Keeping these values clearly organized is crucial before we proceed to the next step, where we will substitute them into our Cartesian formula. Solution breakdown, step 2. Now that we have successfully identified our given values from the previous step, specifically our point coordinates and our direction ratios, it is time to move into the actual substitution phase. To do this, we take the general Cartesian formula we derived earlier, which is x minus x sub 1 all over A equals y minus y sub 1 all over B equals z minus z sub 1 all over C. By plugging our specific numbers into this template, we replace x sub 1 with 3, y sub 1 with -2, and z sub 1 with 5. Simultaneously, we replace our direction ratios of B and C with 2, 4, and -1, respectively. This gives us our working equation. X minus 3 all over 2 equals y minus negative 2 all over 4 equals z minus 5 all over negative 1. Now, as you can see, we have a bit of double negation happening in the middle term, so in the next slide, we will focus on simplifying those signs to reach our final, clean answer. Solution breakdown, step 3. Now, let's move on to the final step of our calculation. In the previous slide, we substituted our specific values into the general formula, but we still have a double negative in our y-coordinate term. So, our first task here is to simplify the signs. Notice that in the numerator of the middle term, we have y minus negative 2. As you know from basic algebra, subtracting a negative is the same as adding a positive, so we rewrite that as y plus 2. After this simplification, our equation looks like this. X minus 3 all over 2 equals y plus 2 all over 4, which equals z minus 5 all over negative 1. And there we have it. This is our final, polished Cartesian equation for the line. Common mistakes to avoid. Now, before we wrap up today's lesson, I want to pause and discuss some common pitfalls. Even if you understand the derivation we just went through, it is very easy to make small errors that can lead to the wrong final answer. First, let's talk about sign errors in the numerator. This is perhaps the most frequent mistake students make. Remember, the formula is built on subtraction. If the coordinate of your given point is already a negative number, you are essentially subtracting a negative, which means the sign must change to a plus. For instance, if our y-coordinate y1 is negative 2, the numerator shouldn't be y minus negative 2, but rather, it simplifies to y plus 2. Always double-check your signs here. Second, be careful not to swap your point and your direction. It sounds simple, but in the heat of an exam, it is easy to get confused. Always ensure that the coordinates of your known point are placed in the numerator, and the direction ratios, b and c, are placed in the denominator. You should never see the direction ratios sitting on top. Finally, we must address what happens if one of your direction ratios is 0. As we saw in our derivation steps, we had to divide by a b or c mathematically. We cannot divide by 0. So, if, for example, the direction ratio, is equal to 0, you cannot write a fraction for the x component. Instead, you must state the x-coordinates separately as x equals x1, and then set the remaining two parts, y minus y1 over b equals z minus z1 over c, as a separate equality. Keep these 3 points in mind, and you will avoid the most common traps in this topic. Key takeaways. First, remember that the Cartesian equation isn't just a random formula. It is directly derived from the parametric equations we studied earlier. The whole process we walked through in the derivation slides was simply about eliminating the parameter lambda from those equations to create a direct relationship between x, y, and z. Second, let's look at the general form one more time. The equation is written as x minus x sub 1 all over a equals y minus y sub 1 all over b, which equals z minus z sub 1 all over c. To use this formula correctly, you must identify your components accurately. The coordinates x sub 1, y sub 1, and z sub 1 represent a known point that the line passes through. Meanwhile, the values of b and c are your direction ratios, which tell us the orientation of the line in space. Finally, try to keep this conceptual intuition in mind. The equation essentially represents the ratio of the displacement from our known point to the direction of the line. It's a way of saying that the change in each coordinate must be proportional to its corresponding direction ratio. All right, we have reached the end of our lesson. Let's take a moment to recap the key takeaways from today's session to ensure everything is clear before you move on to your practice problems. If you keep these points in mind, you'll be able to handle even the trickier problems, like those involving negative coordinates or zero direction ratios that we discussed in our common mistakes slide. Great job today!